Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good day to all. Okay, so this is our first class or first topic in our class. So basically, we are going to look on the construction of the real number. Okay, so basically, if you are interested to look on the history of the real number, you can look on this YouTube video. So it gives you very brief the history of our real number. So now, what we are going to do in our class is we are going to look on the definition of real number, how the real number is constructed. So basically, what we are going to do in the advanced analysis or advanced calculus class, we are going to consider all real number. So we are going to look on the properties of real number, how they are constructed, and what are behavior that we have on the real number. Okay, and at the end of the our course, we are going to look on the most important things or most the famous things that we have in the real number, which is derivative and also integration, that you already learned from your high school until your university level. Okay, so now what is the definition of real number? Right. So we never think of previously. You just take it for granted. So the real number is there. So you just use the real number for your calculation and for your sake of your problem, and you just use is like that. But uh, you have to think as a mathematician. You have to think how the things is constructed based on what are the axiom or what are the condition the real number or some set are constructed. For in our case, we are considering the set of all real number. Okay, now I'm going to give you an analogy. So how you can define a durian here, right? So if I ask you, you will say that. So we can define the durian based on the thorn or based on the smell, right? Or based on the taste, right? So that things or that properties give you the shape or how to say the definition of durian, right? So if I give you, for example, if I give you mango, then you will not say that it is not durian, it is a mango. So even though the shape is not, as for example, in the picture here, we have different shape of durian, but still we call they are still durian, right? And in fact that we have a lot of different tastes, a lot of different texture of durian, but still they are called durian because they share the same properties. So the same thing with the real number. So the real number exists based on the axiom. So what is the axiom? Axiom is just list of the properties that we have on the real number. So of course, the real number, we can do the operation on the real number. Okay, so we have addition operation and also multiplication on the real number. Okay, so this is called the first part of the axiom is called field axiom. So basically we have three axiom or three type of axiom. So first one is field axiom, second one is the order axiom, and the last one will be completeness axiom. So the first one, field axiom, composed of these properties. So the first one is the closure properties, which means that if you add or if you multiply any of the real number, it still will be on the real number. So next one is the associative properties. So these properties mean that if you take the addition of A plus B, then you plus with C, it is equivalent you add A first with the B plus, sorry, if you add B plus C first and then you add with A. So these two things should be equal to each other. And for the multiplication part, if you multiply A multiplied by B first and then multiplied by C, it is also equivalent with the B multiplied by C, then multiply with A. So this we call it as associative properties. So next one is the commutative properties, which means that if you add A plus B, it is equivalent, you take it vice versa, which is B plus A. So the same thing, if you multiply A plus B, it is equal to B plus A. So the same thing. So you multiply 2 multiplied by 5, 5 multiplied by 2, this is also 10. So this is called the commutative properties. And the next one is the existence of additive identity. So what do we mean by additive identity here is that if you add A plus with the additive identity, then you will get A again. So in this case, for additive identity, it is 0, because if you add any number in real number, A plus 0, so you still get A again. So next one is the distributive properties. So distributive properties here means that we multiply A, we combine the operation of multiplication with the summation here. So we can if you learn in your high school, you can open the bracket, right? So here we call this as the distributive properties, where you can multiply A with B plus with A multiplied by C. So we call it as a distributive properties. Okay, so the same like the existence of additive identity, we also need to have existence of multiplicative identity. So for multiplicative identity means that if you multiply a number with that identity, you will get the number again. So in this case, the number or the identity is 1. Of course, when you multiply 3 multiplied by 1, so you will get 3 again. So that number 1 is called identity for multiplication. So here I record again, 0 here is identity for additive. Okay, and the last part is the additive inverse. So of course we have two things here. So first one for additive inverse, and the next one is multiplicative inverse. So what is the definition of additive inverse? So additive inverse means that if you add a number with another number, you will get the identity for additive identity. So in this case, if we add A with the negative A, we get 0. So 0 here, if we call it is additive identity. So therefore here we can conclude A is the inverse for A. So of course inverse in the sense of additive. And the last one is a multiplicative inverse. So multiplicative inverse is that when we multiply with the inverse, when we multiply a number with its inverse, then we will get the multiplicative identity. So we record again, the multiplicative identity is equal to 1. So therefore, when we multiply, for example, 2 multiplied by 1 over 2, you will get equal to 1. So in this case, or in this sense, we got 1 over 2 is the multiplicative inverse for 2. Okay, so I hope so this part, first part of the axiom, we call it as field axiom. So I would like to record again what we are doing now. We are giving the description, or we are giving the properties of the real number. So I record again. So like a durian here, it has its own properties that we can call it as a durian. The same thing that we have for the real number. So for real number, it has their own properties. So what we are doing now, first we are listing, or we are uh, saying about the properties of real number. So the first part of the properties is the field axiom. So now we are going to look on the second part of the properties of real number, which is, we call this order axiom. Okay, so let us give analogy with the durian also. If you take two, for example, durian kampung, and you take another durian, we call this Musang King. So of course, if you ask about the price, the Musang King durian is much more is much more pricey compared to the durian kampung. So in that sense, you can see that you can order the durian, right? Of course, in the sense of the durian, but the same thing that we have in the real number. So you have element of real number, right? So with the together with the elements of real number, you can compare them. Okay, so first one, we have trichotomy properties. Okay, so this property is saying that for any real number, they are going to satisfy one of the following properties. Exactly one of the following properties, which is either A less than B, A equal to B, or A more than B. So this is called trichotomy properties. So for any real number, it has to satisfy the either it has to be satisfied exactly only one of these properties. Okay, so next one is transitivity. So if we have A less than B, B less than C, so it implies that A is also less than C. So you see that here, A less than B, B is lesser than C. So means that A must be lesser than C. So next one is addition properties. So addition properties mean that if we have A less than B, so this is what we have on our hand, A less than B. So next one, we are going to add a number C both sides. So we are adding A plus C here, together B plus C. So therefore, the inequality here will hold like that. So next one is multiplication properties. So if we have from the beginning A less than B and C more than 0. So if we multiply both sides by C, of course the symbol here, the inequality will be whole. So A multiplied by C less than B multiplied by C. Okay, for C more than 0, it will be the inverse if we consider C less than 0. So of course you know this one. So if we have from the beginning A less than B, then we multiply with a negative number. That's why we are going to get A. So the sign here will be turned around, will become bigger than. So this one you already learned, you already practiced during your high school up until now. So what we are doing now, we just give or listing all the properties of their number that actually you are already used previously. Okay, so now the last part of the axiom or the properties of real number is called completeness axiom. So to define the completeness axiom, I will need to have some kind of how to say, the definition. So I need to introduce first that definition or the properties. So therefore I will hold for a while the completeness axiom. So now we are going to define the natural number. So the real number will start from the natural number. So let us give the definition of the natural number. So the set n is called natural number. It it has the following properties. So we start with 1 inside the natural number. So and then we are going to inductively put or inductively how to say construct the set of natural number by this statement. So let's try to understand the statement. If n inside the natural number, then n plus 1 is also inside the natural number. So you can think for a while how to construct, for example, 2 inside the natural number. Of course, you know that 2 is in the natural number, right? So how to construct 2 from the definition here? Okay, so what you can do is that you know that the first statement saying 1 is inside the natural number. So we know that 1 is inside the natural number. So we can take n equal to 1 because we know n 1 is already inside the natural number. Then, so what we are going to do, 1 plus 1. So 1 plus 1 is equal to 2. So 2 is again inside the natural number. So what you have now is 1 and 2. And then how to construct 3 in the real number, the natural number. So you know that 2 is inside the natural number. So what you are going to do is you are going to put n is equal to 2 inside the natural number. Then 2 plus 1. So 2 plus 1 is equal to 3. So 3 is inside the natural number. And so on. So you know that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it will never end. So this is called the natural number. Okay, so now so this is some terminology that you need in order to understand the proving. For me, if you at the end of your course here, at the end of our syllabus, if you can understand these 3 words, you can actually read the proof of the mathematics, a proof in the textbook or in the any textbook or any at least textbooks. So all, sum, and exist. So these 3 terminology are the most important things that you need to understand the proving in mathematics. So all, sum, and exist. Okay, so if let's say that let us consider the terminology from the picture here. So let's say that I ask you to take all the durian. So let's count first. How many we have? 6. Okay, so I count it. I got 26, right? 28. Okay, so all together durian we have 28. So if I ask you to take all the durian, so means that here you can take, you have to take, okay, it is compulsory for you to take all the 28 durian. Understand or not? So if I say that you take all the durian, okay, so that is the first word, all. So sum. So sum in mathematics, 1 is already sum. Okay, so when I ask you to take sum, so you can take 1, you can take 2, you can take 3. So you can take 1 and then give to me. So it already satisfies the statement, my statement. So take some durian. Okay, so that would be the things. Good. So exist here, Exists here means that it is there. So maybe some of maybe you cannot see, but it is still there. So I can give you analogy to understand that exists. How to say? Um, so let's say that you go to a shop and you want to buy durian. Okay, let's say that. So you go to a shop and when you arrive at the shop, you can get the smell of the durian. Okay, you cannot see first. You didn't see any durian, but when you arrive to the shop, you can smell the durian already. Okay, so you can smell only, but you are not able to see anywhere where is the durian. Maybe the keeper hide it somewhere. Okay, and you ask the cashier. So can I? Do you have any durian or not? And the cashier say to you that we don't have any durian, but you can smell very well. So therefore, here what you can say, what you can conclude by yourself, the durian exists or not? Yes, exists, but because you can smell the durian very well. So that's why uh, here you to understand the exist here in mathematics, it is there, but sometimes you cannot see, or sometimes you can see the existence. Understand or not? So these three terminologies are very important for you to understand in order to keep in track the proving in mathematics. Okay, so let us see well ordering properties here. So the well ordering properties say that every non-empty set of natural number contain a smallest number. So if you take any natural subset of natural number, it's always you can find a smallest number in the set. So it doesn't matter how big the natural number that you can take, so it always contain a smallest element. Okay, so this part I'm going to skip first, so I'm going to prepare another video to record again the technique of proving. So I will cover the technique for principle of mathematical induction in that video also. So just recall again the theorem, the mathematical induction. So to prove uh, things or a statement is true by using the mathematical induction, what we can do is we start proving uh, by n equal to 1. So we need to test whether the statement it is true for n equal to 1. So the next step is we are assuming it is true for pk. Then we need to prove it is also true for case k plus 1. So I'm give so this is just analogy for the induction. So when the first, for example here, if I drop the first block here, so all the block will be follow the same thing. So that is the mathematical induction. So when the first step is correct, so the other step will follow the same thing. Okay, so this is an example how we can prove a statement by using a mathematical induction. So first step is to consider n equal to 1. So basically you need to replace on the left hand side here, n equal to 1, we get 1 summation is equal to 1. And then I'm going to consider the right hand side, substituting n equal to 1, simplifying everything here. So of course I don't have to go through very much in this case, in this calculation. So it is equal to 1. So now we are done with the first step. P1 is true. We prove the first one. So next, we need to assume it is also true for PK. So I'm going to use or call the step number 2 inductive step So we are going to assume it is true for n equal to k. So this statement is true already, what I have on my hand. So now we are going to prove it is also a whole, or the formula is a whole for n equal to k plus 1. So what we are going to prove is that this summation is equal to this formula. Okay, this is what we are going to prove, and the first part here, first equation here, is already true from our assumption. So here what I'm going to do, I'm going to prove for case n equal to k plus 1. So for k plus 1, I'm going to divide into two parts here. So first one is j, summation of j from 1 up until k, and then a particular case where j equal to k plus 1 here. So this two right hand side are these two just write in the different way. And then the first part of summation here, I'm going to use the truth statement here, or the assumption that we have here. So I just write k plus 1 over 2 square here, and we write again k plus 1 cube in this case. So what I'm going to do next part is I'm going to consider this expression, and I can see that the k plus 1 is the same expression here. So I can factor out the k plus 1 outside. So of course k plus 1 square, and left inside with this expression. So from this expression, I'm going to consider, or I'm going to open the bracket or open the square and simplify a little bit like this, and then rearrange like this and factor out the numerator here from k squared plus 4k plus 4 equal to k plus 2 over k plus 2 square over 4. Okay, so you can take time, try to rewrite, try to understand all the step here. What I already wrote here is already step by step calculation. So you can try to get you can try to get all the step here. And then from this case, what I'm going to do, I'm going to replace the expression k plus 2 square over 4 into this bracket. So I have k plus 2 square. So of course I start from here, j cube k plus 2 square multiplied by k plus 2 square over 4. So everything's here, I can rewrite into this expression. So therefore, I already proved what I have, what I want to prove for this case. So of course, I take out the square here, so 4 become 2 here. Okay, so we already proved it is also true for n equal to k plus 1. So you can try this example proving by using the mathematical induction. So now last part, or last slide of our this video is on the rational number. So after the natural number, we can construct the integer. So how to construct the integer? So we take all the natural number, and then to construct all the integer, we take the negative part also. So union of the negative part of the natural number with the natural number together with the 0 here become the integer. Okay, so I record again. So we have this natural number, and then we are going to take all the negative part of the natural number. So union these two with the 0 become the integer. So and then the construction of the rational number, it just simply we take the rational number, or a fraction between m and n. So m and n here is in the set of integer where n cannot be equal to 0. So your last part for or your last part of how to say, your exercise for this one, you can prove that the set of Q satisfy the field axiom and also order axiom. So field axiom, so we just recall again. So this is a field axiom and the order axiom is this one. So this is your homework to prove Q, set of rational number, satisfy the field axiom and also order axiom. So thank you for watching.